I have to tell you that I'm quite happy to be here with you in the summer school. And you know that the theme of this school is environmental and resource management. You have listened to climatology, to the last lecture was on energy and low carbon society. And the basic question for me always is, how to determine my own standpoint? Where do I stand with all my life, with all my techniques, with all my actions within the environmental frame? What is going on? How can I measure where I stand? Who is teaching me how far I am away from what we call sustainability? We will have a possibility to discuss sustainability in the workshops. What is it? How to approach sustainability? I will not go into this now. And finally, I worked also for 5 years in Brazil and learned a lot about nature and natural processes. I thought we should look into the governing principles or the main governing principles of nature, of the biosphere, in order to see how nature does its work. How does nature function? And when we understand what nature is doing and how nature is managing its life, maybe we can adapt our techniques to natural processes and to be more sustainable than we are. A very short story. When I arrived in Vienna from Brazil in '79, a technician, an agricultural engineer, came to me and said, "Mr. Blum, I have an idea. Look, we have a lot of animals in soil, earthworms. They are working in the soil, they're making holes. And we are doing this technically with plows and all kinds of equipment. Shouldn't we develop equipment which is adding to what nature, the earthworms are doing and the animals are doing, so we don't need as much energy because they do the job, and we just add what they cannot do or are not doing." And I said, "It's very interesting. Let's start." And finally, we had to learn that the machinery industry was much stronger than us, and they never allowed us to step into an area where we could show how such instruments could be developed. Just for example. Now, I will go and try to explain you the essential governing principles, and then I want to show you give you a very short snapshot on engineering, ecology engineering. You have listened to Professor Novak. He gave you marvelous pictures on how engineering can be done to save energy, and I will just give you a little detailed information how can we use natural processes in the soil, plant, water environment in order to save energy. Now, let's start. The essential governing principles of the biosphere, and if you close the eyes and open it again, you are here in the Amazon jungle. So this is a picture on the Amazon jungle from a tower, observation tower. And if we now going into the forest, it looks in this way. And if we go a little bit downslope here, you find more palm trees, which was it's edaphically different. And the question is, how does this system function? There is no humans interfering, nobody, but the system functions very well. Now, here you have this forest ecosystem, very roughly speaking, and here you have all processes occurring in this system are featured or are supported by radiation from the sun. Everything. There is no fossil energy, nothing. The sun is helping to make the water cycle. This is the precipitation here, comes into the soil, it's taken up by plant roots, it's transported up to the ground, and there are measurements from United States, northeastern part of the United States, in Brook Forest, and they found out that more or less half of the energy which is radiated during the summertime is used only for water transport. Now, this water is furnished again to the atmosphere by evapotranspiration. This is evaporation and this is transpiration here. This is the water cycle. Very close to the water cycle, we have the nutrient cycle. We get also nutrients from the atmosphere. I cannot go into detail here. These nutrients, together with the nutrients delivered by the soil, are taken up by plant roots, transported in the plant, and now we have one solid form of recycling through the leaves and litters and needles. And we have a leaching of the crown, for example, potassium, which goes down, and also we have flow along the main trunk, the main stem flow, we call this, bringing nutrients back. This is a small nutrient cycle during year, and this one here, and this is the large nutrient cycle in solid form. All these processes are nurtured by sunlight. Now, if we ask how does this function, what is functioning in this system, we can say the whole system is solar oriented. Okay, clear. In this system we have closed material cycles. And these materials and the energy contained in these materials are used in cascades. I will take these 2 points and explain this a little bit more in detail. If you look here to this soil, you find here litter. That means dead organic material which has fallen down. It's not in the Amazon, it's in Europe here. And the question is, what's happening here with this material? How is this material transformed again into CO2? You can see it here. We have a lot of animals living in this litter, and they are eating, biting, eating this litter and destroying it, putting it into pieces. And when it's such pieces, others are coming. I will show you. These are the animals, the earthworm and many others. I will not go into detail here. Here you have them living. You have the earthworm here. And then you have a lot of bacteria, actinomycetes and fungi. Do you know how many bacteria you have and I have in my intestine? How many kilograms? 2 to 3 kilograms here in. And without these lively and these marvelous animals, we couldn't even digest one flake, one corn flake, even not one. So these animals have it also, and these are the different forms of bacteria which you see here, and they are finally converting this material again to water and CO2. And here you have, this is the whole distance here is 0.5 millimeter across here. These are very small bacteria here in a soil clump. And in the soil with per hectare and 30 centimeters of depth, we have about 25 tons of these organisms, about 10 tons of bacteria and actinomycetes, about 10 tons of fungi, 4 tons of earthworms, and 1 ton of other soil animals like ants, larvae of beetles, and so forth and so on. And they are working the soil. They are working here on top of the soil, at the soil surface, and they are working in the most upper part of the soil. And of course they are nurtured, all nurtured by organic matter. The food for them is organic matter, like for us. We cannot live without organic matter which is produced by the plants through radiation of sunlight. And if you compare what is in the soil working and living, and you compare what's in top of the soil, then you will see that on the best pasture here in this country, Slovenia, you maximum can have 1 to 1.5 tons of animals, cows, sheep, whatever you, goats, whatever you like. And this would be 2 to 3 livestock units. I will not go into such acronyms. In top of the soil, you can nurture 1 to 1.5 tons a year long. And in the soil, about 25 tons of organisms are living and working. And if this is true, of course, this is something which we can use for different purposes. Now, let's go back. A lot of these animals are, or biota, are living in the soil. Now, I could try to show you more details. This soil has inner surfaces. These are different structures of the soil. And for example, this is at 2 millimeters crumb. These are 2,000 micrometers. And if you enlarge this by 10, you come to 200 micrometers. You see a root here. You see some aggregates. You see hyphae of fungi. And if you enlarge by 10, you see the hyphae cut into here. It's cut hyphae. And you have the bacterium here. You have here different clay materials. If we go to 2 micrometers, you see here microbial debris, and you see also the little clay minerals. And finally, if we go to 0.2 millimeter, you see the clay plates and here different forms of pores between this material. Now, so it looks in the soil. The measure, the scale is here 10 micrometers. And you have large pores here where the water is running very quickly. You have very small pores, and this is a continuum. And also in this space, organisms are living. For example, bacteria sitting here waiting for material coming from the top, which they want to eat. This can be herbicides, fungicides, all kind of stuff. This can be organic, dissolved organic matter, whatever you like. This can be waste material. What is organic, they will attack. Now, these pores we can classify into large macropores. You have it here, small macropores, media pores, endophores, and so on. Here are the small pores. And here you see it once again, the large pores here, the medium pores, and the small pores here. And what is important is that the walls of these pores contain different materials, humic substances, clay minerals, oxides. And this is important for the reactions in these pores between the volume of the pore and the pore walls where these reactions take place. Now, let's go back here. If I enlarge here, we will find the following materials. Here you have a clay mineral. This here is a kaolinite. This here is a gypsite, a aluminium oxide, hydroxide, better saying. And these are the materials. And if you look here to the surface, you will find even organic materials here, some peptides, lignin structures, which are bound to the clay minerals by negative charges. Now, we can also look what these specific structures and electric charges of these constituents are. For example, of clay minerals here, you have permanent and variable charge, electric charge. Oxides have only variable charges, and organic matter have variable charges. That means, if we go back, all these surfaces have electric charges. And these electric charges are able to keep materials. This can be elements, this can be heavy metals, toxic material. When they have charges, they can be kept in the soil. And this is very important to know. And we can use this also as a filter for protecting groundwater, for example. Now, the importance of these pore sizes, which I have shown for physico-chemical and biological soil processes, is that in the large macropores, you have a very good hydraulic conductivity. That means the rainwater is flushing through. Large plant roots and large biota can live in here. In the small macropores, down to 10 micrometers, you have still some good hydraulic conductivity, but only small plant roots can live and grow here. If we go to medium pores, down to 0.2 micrometers, The water contained in these pores cannot be transported by gravity. It's kept in the soil, and this is the basis of our plant growth and of maintaining soil biota in the soil. This water is retained against gravity. And in this space, bacteria, for example, here 0.5 to 3 micrometers large, it's the largest, and 0.45 is the smallest, which I know, can live in this space. But when we go now to small pores, even this water cannot be used by plant roots because it's retained against plant root extraction forces. And we have a lot of soils which contain still 20% of these small pores. That means high quantities of water are fixed in the soil. And this is a basis. If you have a very dry soil, you still have here water, which is evaporating, and so you have humidity in the soil. The humidity of soil never goes down lower than 95% of humidity, and this is a basis for many animals to live there, like earthworms, for example. But what is even more important, in these small pores, no soil organisms nor roots can live because it's too small. And this is a space where we looked for a long time in order to understand what we call hidden residues. Hidden stuff, organics in soil, pesticides, all kind of pollutants, which we couldn't explain where they are, but we could measure them. Because if they enter this space, they cannot be destroyed. They cannot be destroyed or mineralized or metabolized by soil microbes. Now, let's go a step forward. I calculated here the inner surface, the maximum theoretical surface of a soil volume of 1 hectare, 100 by 100 meters, and 20 centimeters of depth, with a bulk density of 1.5 tons per cubic meter. 100 by 100 by 20, 0.2 gives 2,000 cubic meters multiplied by 1.5 is 3,000 tons of soil material. So if you want to transport from 1 hectare 20 centimeters of material, you have to move 3,000 tons. And if we assume that this soil volume contains 20% of clay minerals, and these clay minerals have a surface per gram. Gram is half a fingertip. With 200 square meters per gram, and 20% of 3,000 are 600 tons of clay minerals, you come to 120,000 square kilometers. And if you think that this, and this is very often the case, 3% of organic matter we have in this soil, with 1,000 square meters per surface per gram, 3% of 3,000 are 90 tons, we get 90,000 square kilometers. That means in a cutout of 1 hectare and 20 centimeters of depth, we have the surface of 210,000 square kilometers. Now the total land surface of Slovenia is 20,273 square kilometers, and this is contained in a soil volume of 31.2 meter by 31.2 meters. This is just a corner of a sporting field, and 20 centimeters of depth. This gives here 97.3 square meters. So what the mystery of the soils are, they have enormous inner surface, It's just unimaginable. And all these surfaces have electric charges which depend on pH or don't depend on pH, just by the structure of the different materials which form these soil pores. Now, the question is, what are these ecological functions? The first one is the biomass production. I will not go here. This is, of course, normally a natural process close to the principles of nature. Solar energy, but biomass production nowadays in agriculture is by far not depending on solar energy. It's depending on fossil material to a great extent. It's on fertilizers, especially nitrogen fertilizers, and many others I will not go into detail. So even in biomass production, we are already far away from a sustainable system. And this is unfortunately to say, I have to say, for all Europe. There are nearly no, maybe some organic farmings, but it's only very specific ones are close to sustainable systems in the sense of energy. Now, the second question is filtering, buffering, filtering, buffering, and transformation between the atmosphere, groundwater, and the plant cover. And here we go to the next picture. All input coming as solid, liquid, inorganic, organic compounds into the soil can be treated in the soil by 3 different ways. By mechanical filtration in the pore space, I've shown you the pore space, and this can be solid or liquid compounds. Second is a physico-chemical reaction by adsorption and precipitation on these surfaces with electric charges. Adsorption and precipitation is a kind of buffering. And finally, transformation through alteration and decomposition, that means mineralization and metabolization through the microbes or biota living in the soil. And we have enough of them in the soil for transformation. So we can use soil by preparing soil in a specific way to fix pollutants, to get rid of pollutants, especially organic compounds, but we can also try to get rid of inorganic compounds. And as long as the soil maintains these 3 functions, there is no danger that this stuff comes into the soil's water, the solution, and is taken up by plant roots or washed out into the groundwater, harming our drinking water resources. This was filtering, buffering, and transformation, and the soil as a biological habitat and gene reserve I have shown you. Now, the processes, all these processes occurring in the soil can be here in this soil. These are the soil biota, the vegetation based on solar energy here, the hydrosphere and the pedosphere. All these processes can be used for different kind of ecological engineering. And here I come to the ecological engineering. And we have 5 main soil parameters for this ecological engineering. As I have shown you, the total inner surface of the soil, the constituents of the inner soil surface, with their specific structures and electric charges, the soil organisms, the pH and redox potential of the soil solution, and finally soil temperature, which means energy available for the processes. But what do we mean with ecological engineering? What is it? And this means managing natural and anthropogenic resources by using natural processes. And the slogan is, let nature do the job. Not humans, let nature do the job. And this, of course, means to save a lot of energy, because these biota are there, the plants are there, the biota in the soil are there, the space is there, the electric charges, the self is there. We have many, many, many parameters which help us to let nature do the job. And what nature cannot achieve alone is done by technical human interference. I will show you how this functions. And there are 3 main principles. We are using energy close to natural systems, for example, direct solar energy, radiation, or indirect solar energy, which is organic matter. Organic matter is nothing else than a condensed form of solar energy transformed by plant photosynthesis. This is very important. We use energy close to natural systems, and this is mainly solar energy. The second principle is that all the processes are self-organized. If we arrange a certain frame where these soil biota can work or plants can work, then these natural processes are organizing themselves according to their phylogenetic forces and power behind. because they dispose, if we let them have no shadow, the necessary energy to be used. And what we are doing, and this is the third point, we are pre-adapting these systems through selection of species. We are, for example, type of bacteria, type of plants which we use, type of the depth of soil where we let work these animals, or that's biota. Pre-adaptation through selection of species and creation of adequate ecological conditions, that we loosen the soil, or physically that we give certain, we change the pH, that the biota, the bacteria are like to work, start to working, or biological conditions in different ways. Energy close to natural systems, self-organization of the processes. And finally, what we are helping is a pre-adaptation through that we choose the right species and give them conditions where they can start. Please, if I'm too quick, if I'm too complicated, because I know some of you are not coming from soil science or from biological sciences, maybe you come from other chemistry or what, I don't know, or economy or whatever you are coming from, please raise your hand and ask me a question. I prefer to have the questions during my lecturing. If you have questions, please put them forward to me. Some examples for ecology engineering. We have two types in principle, preventive and structuring ecological engineering. That means we are trying to avoid problems to arise. For example, that we have no leaching of herbicides into open waters. We have no problems of liquid waste, for example, from houses, black water problems, used water problems in hydrological systems. Or we are trying to improve the landscape or riverbeds by planting, by structuring, and these are all ecological engineering purposes. Another one would be curative and remediative ecological engineering. We use ecological engineering for remediate pollution, for remediate accidents which happen somewhere. Preventive and structuring ecological engineering. First one, we are structuring aquatic systems including wetlands. For example, ecological stream restoration by vegetation. After Second World War, after 1950, let's say, engineers started to create artificial waterways. They made channels paved with stones in order to get very nice little rivers, and the problem was finally that they dried out the landscape because these waters were running out of the landscape very quickly into the sea or somewhere else, and the landscape became dry. Now we saw that this was the wrong system, and we tried to make meandering systems in order to keep the water in the landscape and to have also a vegetation type which is adequate to the certain landscape in the sense of landscaping. Another possibility is to create stormwater basins, or what we call stormwater management in urban or peri-urban environments. And this stormwater management will be more and more important in the future because, as you know, or as you are perceiving, and we are perceiving every day at the moment in Europe, the meteorological events, not climatological, meteorological events are getting more extreme, drier, hotter, and wetter, and this in a short time distance. That means very heavy rainfalls in a short time distance. And here we need stormwater management in urban and peri-urban systems, environments, in order to avoid damages in houses and all kind of urban and peri-urban infrastructure. Reinstallation of beaches and mangroves for coastal erosion control and protection. Maybe you remember this big tsunami which happened some years back. in Asia. And we could recognize that where we had still mangrove, the damages were very small, but where they had cut the mangroves in order to have nice beaches for tourism, they had some tremendous problems. So the question is how to reinstall beaches and mangroves for coastal erosion control and protection against tsunamis. This is a typical question of ecological engineering. And finally, structuring of wetlands for different purposes, for example, water purification. I think I have a picture here. Here you see a dam. This is a dam here. These are large agricultural areas here. And from these large agricultural areas you have erosion material coming down, especially pesticides which are used here are coming into the waters, and we are trying to keep these pesticides here for biological control. We are decomposing these herbicides in different systems. I give you an example. The basin which you saw was the first one. Here was a dam. Here you have this, what we call is a constructed wetland, where materials coming in are purified. Then you have a spillover, and you have a second little basin, artificial basin, constructed wetland, where you finally purify all the stuff before it leaves to the right side here. Come on. To the right side here, to the open rivers. This is typical ecological engineering. Protection of landscapes, including settlements against landslides, erosion, and avalanches. Reforestation, forest structuring, forest protection, plantations in mountain areas, certainly also in this country here. Erosion control in agricultural areas, contour stripping, all kind of stuff. I cannot go into detail here. Plantations for groundwater control. Very important example which I can give you from Western Australia. They cut down in Western Australia eucalyptus forests because they wanted to convert forest land into agricultural cropping areas. And they did this, but they didn't study this ecological situation before they cut down the eucalypts, because the eucalypts had used the groundwater, which is saline, naturally saline, and pumped it out. So the saline water could not come into capillary rise to the top of the soil. When they cut down this biological pump of eucalypt, the groundwater level was rising and came about 40, 50, sometimes 60 centimeters to the surface. And then through capillary rise of the salty water, you get salt crusts on top of the soil. Many, many thousands of square kilometers of cropping areas are now salty, and there is no way to remediate this system, because you would need to reinstall forests, and how to reinstall forests on saline surfaces. Maybe you could use some tamarisk species or some others, but this is very costly and very difficult. And at the moment, this started about 10 to 15 years ago. Until today, there is no remediation possible for this. We need plantations for groundwater control if we can install these plantations through ecological engineering, just as an example here. Management of solid and liquid waste.
Just a question.
Yes, please.
Plantation for groundwater control.
Yes.
So, I mean, at the end of the day, I thought eucalyptus is drying out the soil. So, how can it be good?
No, eucalypt is using a lot of water. Groundwater is evaporating water and transpiring water, pumping it out. If you leave eucalypts, it may be you can do between patches of forests agriculture, because the forests are pumping and avoiding that the groundwater level is rising too high to the surface. You understand what I mean? Okay. Other questions? Though these are measures, we are not digging big pumping stations, big channels for salty groundwater, with pumping stations, pumping it 100,000 of meters, kilometers, not thousands of kilometers, but hundreds of kilometers somewhere to the seaside. We are using plants to evaporate, and that's it. And then they keep the system under control. Management of solid and liquid waste. Composting of solid waste is one kind of ecological engineering, and there are many forms of composting. I will not go into detail. Probably you know how this functions. Composting is reducing the volume, is creating very promising organic products which we can use in agricultural or gardening, agricultural production or gardening. Reuse of sanitary landfills by ecological treatments. Now, I don't know if you know that you remember the Olympic Games in Sydney? Olympic Games in Sydney, some 10 or 12, what, 2000 I guess. Yes. All these places are on landfills. Nobody knew that. It's not nice to run 100 meters on a landfill, on a waste deposit. But what I did, they put soil material in top of this in such a way that the soil material was filtering the gases which came from below, oxidizing these gases, for example, methane and other materials, other gases, thus avoiding that this stuff comes up to the atmosphere. And the technique to make covers on waste deposits, on landfills, is a kind of ecological engineering. Here I wrote ecological treatments, because in many parts of the world there is no space left except landfills where you can, when you use the ecological engineering, you can use these landfills for different purposes. Soil fabrication based on waste material. We can also produce new type of soils, artificial fabricated soil based on waste material. We can purify wastewater by ecologically by soil management. I give you an example here. Here you have a little house somewhere, and in remote areas you have a lot of those huts, hunting, for fishing, for recreation. But these people living here need water, so they dig a well here, and this is the groundwater here. But at the same time, in the house, they produce wastewater. And the question is where to go with this wastewater, because if you let the wastewater just percolate close to the well, within short time distance you get polluted water and you cannot use the well anymore. So what you can do is you produce a septic tank. You are sedimenting the solid materials in the septic tank. You have an overflow, and then for this overflow, with a lot of organic stuff, even microbes in it, you are preparing a kind of filter bed. Here it's a kind of subsurface disposal system, a filter bed. And in this filter bed you have microbes, organisms, which are mineralizing, that means totally decomposing organic substances, also polluting organic substances to CO2 and water. And
Would that be composed out of this filter pit?
Pardon?
What material would this filter pit be composed out of? Would it be sand or
You need a system which, where you have enough oxygen in. So this is a kind of coarse filter material, gravel and sand, which is intermixed. And in this part, you get already a microbial decomposition. And then what is not kept here is filtering in the soil here. And in this soil, you have another organisms, biota, which are then finally decomposing all kind of pollutants. So when this stuff comes down to the water table, it's clean. And this is a solution which, and here you have this, the tube which comes from the septic tank is here, This is the effluent, septic tank effluent comes here, and this is a cross section. This is a tank, and it's filtrating here in this kind of material here, where these microbial processes take part or take place. Structuring of ecosystems. We can create parks, planting of trees, shrubs for specific purposes, for example, as wind shelter. A lot of possibilities exist in the preventive and structuring ecological engineering system. When we go to the curative and remediative ecological engineering, we have different topics here: ecological restructuring of damaged landscapes and soils, improvement of natural attenuation, I will come back to this a little bit later, or bioremediation of contaminated soils, either by phytoremediation with plants or microbial remediation without the use of plants. And these are very promising processes which we are using already, and this all is ecological engineering. I have not prepared now slides here in detail because I thought I should give you an overview and then we go to discussion, because we should see how we manage this ecological engineering in the context of the whole course here. Improvement of natural attenuation means that we prepare soil in such a way that elements, for example, heavy metals, can be kept in the soil by changing pH, for example, by using calcium carbonates, by using all kind of alkaline, earth alkaline elements in order to raise the pH. This would mean that in this case, through raising the pH, the soil can keep elements in the soil which are not washed out and come into the groundwater. Bioremediation of contaminated soils, phytoremediation, means that we are planting specific plants which are accumulating, for example, metals, heavy metals. We have different plants which can absorb up to 1% of the biomass in heavy metals without dying. That's very important. They are just able to, for example, copper or zinc or other elements. These plants are absorbing these elements, and then we cut the plants and bring the plant material to an incineration plant where we get ash with these elements and they will be deposited under controlled conditions. If we do this for a certain time, we can remediate soils, we can take out heavy metals out of the soil by plants, by phytoremediation. Phytoremediation is even better for organics because in the case of organics, in the rhizosphere, in the sphere of the roots, a lot of bacteria are living which can decompose organic matter totally to CO2 and water. And this means that these organics don't exist anymore after purification or remediation. In the case of microbial remediation, without the use of plants, or let me go back to the phytoremediation, the advantage of phytoremediation is also that the plants are absorbing radiation, solar radiation, though they are bringing energy into this absorption and remediation system by solar radiation and the fluxes of plant material, plant material produced by photoassimilation, and this material in the root system can help to remediate contaminated soils. Another form is microbial remediation without plants. In this case, we use specific bacteria, which are known. You can buy it now, those bacteria in the market, on special markets, for oil spill, different type of oils, pesticides. You put these bacteria, You give them a starting component, for example, easily mineralizing sugars or kind of easy mineralizable organics, and they start and then they decompose totally these oils or these herbicides. This is possible. And all oils, all organics are decomposed. The only question is, how long does it take? And this is much easier under terrestrial ecosystem, in terrestrial ecosystems than in water ecosystems. Maybe you remember this large accident with the tanker Excon near Alaska, where you had hundreds of kilometers of beaches polluted with oil components. If you go there now, this was about 10 years back, you don't find anything anymore. It's all gone, because microbes are decomposing this stuff. And finally, somewhere it's finished. The only question is, can we wait until nature does this, or should we help nature to do it quicker? And this is exactly what we are doing with microbial remediation. We bring starting conditions to these microbes, which enable them to react very quickly and to remediate the sites. Conclusions and outlook. What can we say? When we try to use the basic principles of natural systems and use this for ecological engineering, we can save a lot of energy. We can do it with the help of solar energy, with the help of the existing soils, existing landscapes, the existing materials around us. We only have to be tricky and clever enough to combine things in a way that they function. And if I go, maybe I can. Back again to the essential governing principle of the biosphere. So far we have discussed solar orientation, closing material cycles, and use of energy and material in cascades. One further point what nature does is concentration of surplus. Nature never dissipates. And some time back, we tried to follow the policy of high chimneys. That means when we had polluting fabrication or industrial processes, where we got a lot of pollutants to the air, we built high chimneys because we said then this stuff is spread over large areas, dissipated. After 10 years, we recognized that this is a very short-minded attitude, because it's only dissipate, and you find it somewhere. It's diluted, but with time you are accumulating this stuff. Nature never does something similar. Nature, for example, is concentrating always. If this would not be the case, you would never find quartz veins in the rocks. You have quartz in the rocks, quartz veins. You have in the rocks also silver. You have gold mines. You have all kind of stuff. And these are all elements which could not be put into the crystalline structure of micas, of feldspars, of other kind of pyroxenes and other kind of minerals. And so the nature concentrated it in certain parts of the rock and did not dissipate it. Gold is never dissipated in a whole mountain. Silver is not dissipated in a whole mountain. Manganese is not dissipated, iron and so forth, quartz, silicon. It's always concentrated. And this we have to learn from nature. Even today, on the bottom of the sea, manganese knots are formed, always as knots and not as a dissipated mud on large areas. Concentration of surplus, no dissipation. Another feature of nature is that nature works with a maximum variety. Maximum of biological, chemical, mechanical, and other options, especially biological options. Maximum variety. if we obey or if we follow this principle, we could not do agriculture. Because agriculture is a use of one plant, of wheat, of barley, of maize, corn, on large areas. This is monoculture. This is not a maximum variety of plants on a certain space. In order to compensate this problem, we have to use pesticides in order to combat enemies who are happy if one starts to eat corn or maize. All the maize is eaten. If you would have here a maize and here some other plants, the danger that the whole system would be destroyed in a short time distance would be just minimum. Therefore, nature always works with a maximum variety. And finally, nature is networking in decentralized systems, which also is enhancing ecological stability. I repeat once again, solar energy, which is reducing entropy in the system, closing material cycles, use of energy and material in cascades, concentration of surplus, minimizing entropy production, and finally, the maximum variety and the networking for enhancing ecological stability. I won a big prize in a discussion with the Minister of Ecology of Brazil, Lutzenberger, in a meeting in Salzburg in Austria, and we were discussing and said, modern agriculture is not natural. Of course, it's kind of natural, but it's a system where humans selected in order to get enough food, one plant and put it on a large area. And you will never find a natural monoculture with annual plants. I'm not talking about perennial plants. For example, reed beds on large lakes and waterways. This is something different. But you will never find a monoculture with annual plants in nature. Never. This was specifically created by humans in order to enlarge or increase food production, which was urgently needed at that time when they started this kind of production, but it's not natural, and in order to protect it, we need a lot of energy to maintain the system. So this is once again, these are the essential governing principles of the biosphere, and now you can decide where we stand with many, many different actions which we are doing every day in our environment, in industry, in our households, in our direct environment. And I think this is a very interesting measure in order to judge where do we stand when we talk about sustainability. And let me say this as well. Sustainability can only be defined on a case basis. If you take a farmer who has two different cropping fields, one cropping field on a flat area, and about 100 meters away, a cropping field on a slope with 30, 40 degrees. This farmer can never produce food on the slope in the same way as he produces on the flat area, because on the slope he has to make counter-erosion measures, he cannot use machinery, and so forth and so on. Though the price for this material which he is producing must be different. But this is a problem on a world market. If you have one world market price, then of course these people have to struggle in order to find a way to make their living. So sustainability means to sustain this system in a flat area. It's much easier than on a slope. If you want to do maize cropping or wheat cropping or whatever you like. And therefore, when we talk about sustainability, we have always to ask where, how, and under which conditions. And then we can decide what we think would be interesting to define in order to be sustainable. And for this, again, we can use these essential governance principles of the biosphere in order to decide where are we, where do we stand? Are we on the right side? Are we developing in the right direction?